Let me refresh your memories. Query languages take a set of relations as input and produce a relation as output. We have already seen relational algebra. Today we will focus on relational calculus. While relational algebra was procedural, relational calculus is declarative in nature. There are two types of relational calculus, namely tuple and domain relational calculus. We saw why relational algebra is procedural. Today we shall see a non-procedural version of query language. One interesting feature is that both relational algebra and relational calculus have the same expressive power. A small story for you. The word calculus comes from the root calculi, a Latin word for stone. History tells us that we used stones for calculation. One stone to refer to one, and two stones refers to two, and so on. The problem is that counting large numbers would mean we need to carry huge sacks of stones. Okay, I'm kidding here. In tuple relational calculus, a query describes the tuples we need. In that sense, it is descriptive. So we are not talking about how, but we are talking about what we need. We write it as shown here. So we say we are interested in all tuples T that meet the predicate P involving T. So here P of T is a predicate involving attributes of T. Uh, it, uh, it is the set of all tuples T that the predicate P is true for T. So that's the output for this entire tuple relational calculus expression. If you remember predicate calculus, P of T is very similar to it. Here is an example. Um, what if we want to output uh, so uh, so so here is an example. Let's say we want to find all tuples from instructor relation whose salary is greater than 80,000. Then this is how we would do it. So we are interested in tuples T such that T belongs to instructor and T's salary is greater than 80,000. What if we want to output only few attributes, something as in the project operation we saw in relational algebra? We do that using this syntactic structure. Imagine that we are copying the contents of the relations instructor into S, and filter S as indicated by the predicate. So in this example, we like to keep all those tuples of instructor in S where salary is greater than 80,000. The assignment tells us that the output relation should contain only the ID attribute. If we are interested in other attributes, we would have included them as T of, let's say, name equals S of name and so on. In the conjunction here. So we keep adding conjunctions for all those attributes that we are interested to get as output. Uh, a TRC formula has the following components: variables, quantifiers, logical connectives, comparison operators, and constants. Let's consider a problem. Um, Consider the following relational schema involving students, courses, and registration. Assume this is given to you. Now, find the distinct names of all students who scored more than 90% in the course numbered 107. So, this is what we want. And this is what we would write as a TRC expression or a TRC query. So, we are interested in all tuples T such that there exists some S in students and there exists some R belonging to registration. So assume I have a copy of S from students and R from registrations. S dot roll number equals r dot roll number, and r dot course number is 107, and r dot percent greater than 90. So these two conditions reflect what is given to you. The students must have scored more than 90% in the course numbered 107. So course number is 107, percentage is greater than 90. So these two are obvious. Now let's look at the other conditions that we are interested in. We are only interested in names. That's why we have t dot s name equals s dot s name. So this condition copies the result of matching this from t to s. So t dot s name equals s dot s name, and we also carry the roll number. So we have to have a join relation between students and relations. So the way to join them is using the roll number. So recall your theta join understanding, where we take the primary key to join two tables. So here I'm joining course and person. So course and course and registration is joined to I'm sorry, students and registration is joined through roll number. So I have students roll number here, registration roll number here. So I'm joining these through roll number. And why I need students? Because I need the student name. And why do I need registration? Because that's where I have course number and percentage information. And finally, I am only interested in the names. So when I select the tuple t, I'm only interested in t dot s name, but I copy s dot s name from the result of this predicate into t dot s name. So assume that's what is happening, and only those names would come out as output. These names are guaranteed to be distinct. That's because the output is a set. um, so that works for this question. As you must have observed, TRC expressions are built with atoms. So we call each part of the expression as atom. For example, here is an atom, here is another atom, and these two are related through a conjunction that makes it a atom of atoms, and so on. So that's what we call as a formula. Um, so atom at the very basic form has the following form. Um, S belongs to R, or S of X and U of Y are combined through some operation. The operation could be any comparative comparison operation, and we could also use a C in place of one of the operations. Um, we can recursively apply this to now construct the formula. Atom by itself is a formula, and if let's say p is a formula, then not p is also a formula, and sometimes we might want to nest a formula inside a formula, so we use parenthesis. So if this is a formula, then we could use quantifiers, as there exists s belongs to r on p of s is another formula. We could use existential quantifier, we could use universal quantifier, and so on. So now, so thus we could construct more complicated formulae for TRC. Okay, let's quickly review the first order predicate logic. So this is school stuff, so I might go a little fast here. Um, there exists a y for all x such that loves of x comma y. So if we know that loves of x comma y is a predicate which says that x loves y, uh, then there exists a y for all x such that loves of x comma y says that there is someone who is loved by everyone. Then how would you write everybody loves somebody? Well, for all x, there is a y such that loves of x comma y holds true. That says everybody loves somebody. How do you say everyone has someone who loves them? Everyone, for all y, there is an x, right? So for all y, there exists an x says that loves of x comma y holds true. There is someone who loves everyone. There is someone who loves everyone. There exists an x for all y such that loves of x comma y. So this x loves everyone. Okay, so it's fun to study predicate logic. So I recommend that you spend some time practicing the basic quantifiers so that you understand how to use them in framing queries. So here is another example. For all x, whale of x and mammal of x. So everything in the universe is both a whale and a mammal. That's what we are trying to say. Of course, all this depends on the semantics we associate with these predicates. So whale of x, what does whale of x mean? So it's up to us to define what whale of x means. So here I mean to say that X is a whale, and that's what is reflected in whale of X. So mammal of X is true if X is a mammal. Mammal of X is false if X is not a mammal. Okay, what does this expression say? Um, so owns Mary, comma x implies cat of x. So let's say owns of two parameters returns true if the first parameter owns the second. So Mary owns x. Okay, so if Mary owns x is true, then that implies that x is cat is also true. So in other words, all Mary owns is just cats. That is, everything Mary owns is a cat. Also true if Mary owns nothing. Okay, so that's a small nuance that you should pay particular attention to. It's possible that Mary does not own anything. If she owns something, then it must be a cat. So this is the implication relation that we use here. There are several identities of use in this context. For all x not p is equivalent to saying there exists no x with p. Also, not of for all x p is same as writing there exists x such that not of p holds, and so on. Please take a moment to read and understand these identities. These are useful to convert one expression into another. Um, we could also break or decompose the expressions. For example, for all x, p of x and q of x is same as writing for all x, p of x and for all x, q of x. Both are equivalent. The same for existential quantifier too. Okay, so now we understand the basic predicate calculus. Let's put relations into them. So in effect, what I'm trying to do is I'm going to treat these x's, all these variables, as relations instead of values, as we saw in our predicate logic class. So here we look at these variables. So in this case, s refers to a relation and not to a value anymore. So that's where relational calculus kicks in. Okay, so let's assume this table is given to you. A tuple T exists with ID as 15151 in this table. Now, um, let's say I'm interested in this expression. So this is what we would write. So there exists S that belongs to instructor table. So there exists an S belonging to the instructor table such that S of ID is 15151. So notice that I'm referring to an attribute of S through S of ID. Yeah. So the S itself belongs to instructors, such that S of ID equals 15151. So if I put this predicate, then I am left with only a relation with only one tuple, and that relation is the output of this logic statement. So note that we are describing what we want using logic statements, and that is what TRC is about. What if we are not interested in all the tuples but only particular columns, particular attributes, let's say ID? Then I would change this to look something like this. Basically, I'm doing an and, so there's a conjunction here, and I'm adding another predicate, which is T of ID equals S of ID. So finally, whatever is equated to T is what gets into the output. So now I know that T has only ID attribute. This is just a syntactic structure to uh, mention that we are interested in only a certain attributes. Here is another example. What would you do if you are interested in all instructors, in saying that all instructors earn more than 10,000? So if you want to say this, then for all s belonging to instructor, s of salary is greater than 10,000. That's simple. Let's move on. No instructor works in Edison building. Can you give me a logic expression for that, or see if this logic expression is correct? So, so we want to check no instructor works in Edison building, right? So for all u belonging to instructor and for all v belonging to department, the following constraint should hold. hold. Um, U of department name is same as V of department name. So that's our join condition. So we are doing a theta join on the column name department underscore name. And after joining them, we do V of building is not equal to Edison. So if V of building should not be Edison. And this should apply to all instructors and across all departments. So when you join departments and instructors, then the V of building, so the resulting building column of V should not have any addition in it. So that means there is no addition at all in our relation. So here's another example involving multiple relations. How do we say any instructor with salary greater than 90,000 works in Taylor building? So there exists an instructor U belonging to instructor with salary greater than 90,000, and I could do for all V belonging to department U of department name equals V of department name. That's my join condition. And after joining, V of building is Taylor. So V of building is Taylor, right? If this holds, so this means that any instructor with salary greater than 90,000 uh, works for uh, works in the Taylor building. Okay. Um, yes. So let's change it a little bit. What would you do to mention that no instructor in Watson building earns more than 90,000? So you can use a not operator here. So let's see if you have understood things correctly. Um, which of the following TRC expressions is or are equivalent to for all t belonging to R of P of t? So clearly R is a relation, P of t is the predicate that we apply on that, and T is the set of tuples that we are interested in. So here there are a bunch of options. So I urge you to go back to the identities, these identities that we discussed, and if you apply those identities, the answer should be pretty evident. So the right answer is there exists no t belonging to R such that not of P of t holds. If so, the complement of P of t would be not of P of t, and the complement of for all t would be not there exists any one t. Right. So this is the same as writing not exists any tuple t belonging to R such that not P of t holds. So logically they mean the same thing. There's another small concept which is very useful to know. Not when we use these kind of knots, we get into a issue. Not all tuple relational calculus expressions are safe, as we say it. For example, I know that give me, if just ignore this not for now. So if this simply says t such that t belongs to instructor, then I'm interested in all tuples in instructor, which gives me finite results, right? So in any relation there would be only finite tuples, so I get finite tuples as output, so that is understandable. But what does this mean when I say not of t belongs? So give me all tuples that are not in instructor, what would you do? Yeah. So we call so that the domain of that could be infinity, and we call that as unsafe expression. Okay. Now to avoid getting into these kind of situations, I use an operator called, or a function called domain. And when I pass anything to domain, it converts unsafe expression to safe expression. In other words, it takes the universe of um, uh, the current domain. So in this case, it's instructor table. So takes all the tuples in instructor table and subtracts what is given. So if you want not of let's say all tuples in the instructor, so then I take all tuples from the instructor and remove it from the universe of instructor, and I give you an empty relation out. So that way, this domain operator makes querying safer. Um, so consider this schema where I have two tables, employee and department, and a bunch of queries are given to you. Which of the above queries are safe, do you think? Please pause the video here and take a look. Well, we don't see any not operation anywhere here, and we are well within the domain when we are doing all these operations. So all these queries are safe. That was a tricky question. Um, let's move on now to domain relational calculus. Just like how we saw tuple relational calculus, there is another way of expressing what we want, and that is domain relational calculus. If you look back at tuple relational calculus, the way we used to project certain attributes was a little counterintuitive, and domain relational calculus makes that part a lot easier. So here we simply say that we are interested in x1, x2, x3 up to xn. So we are interested in these attributes such that some predicate on those attributes hold. So that's all there is with the domain relational uh, calculus expression. Let's take some examples. So let's say I'm interested in ID, name, department name, and salary um, from instructor, and such that salary, which is S belongs to salary, S is greater than 80,000. So this is how I would write a domain relational calculus expression. You see this is much more intuitive and a lot easier to write, because we specify which columns we are interested in right here. Going back to TRC, we would have just put a T or a S over here, and then we'll have to do T of S equals S of S or something like that, which makes it a little non-intuitive to follow. So if in this case I'm interested only in I would simply do a I here and drop the other columns. So rest of the things remain the same. So apply this entire predicate, but output only the ID is what I'm trying to say here. um, the safety problem appears here as well. So you cannot write something like this. So give me all I such that I doesn't exist in instructor, doesn't make any sense, and that's why we call these as unsafe. And again, once again, you could use a domain operator to convert these to safe queries, where you at least at the worst case get empty results and not something and you don't ask something which you don't know. Okay, now let's take our familiar example of finding distinct names of all students who scored more than 90% in 107 course. How would you write the same thing in domain relational calculus? Please pause the video here and try it out yourself before I move on to show the results. Here's how I would do it. Let's take the easy part first. So we say that RP is greater than 90. So that's easy. Um, and let's see what is happening in the first part. So I have SR, SN, two variables belonging to students. All right, and then I have SR107 RP belonging to registration. Now, the way to read this is by mapping these tuples to the schema that you have. So we know students schema has roll number and student name. So the order is important here. So I have roll number first and then the student name. So SR refers to roll number and SN refers to the student name. So I have roll number and name captured in two variables SR and SN. Now SR SN belongs to students and SR belongs to student. Some student roll number fits here, and I hard code the second part of registration. So registration has roll number, course number, and percentage. So roll number is SR, course number is 107, and the percentage is RP. Now SR107 RP belongs to registration. So only pick those tuples. Okay, so such tuples will have some SR values and some RP values. And we also fix RP greater than 90. If this was a value, a constant value, I would have just replaced RP with that constant value. But since we want something greater than 90, I would add another conjunction and say RP greater than 90. And when I put together all these three, there exists some SR and there exists some RP such that this holds true. And I am interested in all such SNs where this holds true. I hope this was clear. If not, please go back and review this slide and hopefully DRC would be clear to you. And not only that, hopefully you would find DRC expressions being much easier and simpler than the TRC expressions. A fact worth sharing with you is that any query language as powerful as relational algebra is called relationally complete, and relational calculus, restricted to safe expressions, is relationally complete, and they have the same expressive power as that of relational algebra. However, here is an interesting fact. SQL is not relationally complete. SQL allows duplicate rows, so not relational at all at the first place. No zero attribute relations are possible in SQL, but theoretically that's doable in relational algebra. Complex queries such as the ones we've seen need sometimes loops or iterators in SQL. So there are many of these reasons for which we say SQL is not relationally complete. That's all there is for today. Thank you.